by Olivier Debarre from Paris, and he's going to talk about non-smoothable cycles on algebraic varieties. Please.
Thank you very much. Thank you for the introduction, and thank you for thanks to the organizers for inviting me here. So I will talk about non-smoothable cycles on algebraic varieties. It's sort of a complement to Claire's talk this morning. And what's new in this talk is joint work with Olivier Benoit. So Olivier Benoit was a former student of mine. He was also the PhD director of Olivier Debarre. I was also the student of Arnaud Beauville, so it's all a family affair. Okay, so let me recall some things that Claire mentioned this morning. And maybe I will start with the question of smoothability of cycles on the C-infinity manifold. So maybe the story starts in 1954 with a famous article by René Thom. He was a professor in Strasbourg at the time. And so the title of this article is Quelques propriétés globales des variétés différenciables. He wrote in French also. And so the question that was also mentioned in Claire's talk is when... Okay, so the ambient variety, okay, so when is a homology class? You were thinking more in terms of homology classes. When is a homology class on a C-infinity? So differentiable means C-infinity. Orientable real manifold. Represented in the sense that Claire explained this morning by a orientable submanifold. Okay, so manifold is equals smooth. So okay, it's a long article, it proves many results, and so one of them is that any class has a non-zero multiple which is represented by a submanifold. And also, so something that has maybe little to do with what I'm going to talk about, but still it's interesting, I didn't know that. Some classes are not, cannot be realized, are not images of manifold by a continuous map. No, no, yes, yes. So there's no linear combination, it's just the class itself. So I want to translate these kind of questions into the algebraic geometry setting. And so now X will be a smooth projective complex variety. So, and I denote by n its dimension. And as Claire explained this morning, every subvariety of algebraic subvariety of X, even singular, has a cohomology class. Okay, so same notation as in Claire's talk this morning. D will be the dimension of Z, and C its codimension. Okay, and the class that can be so represented, or linear combination of these classes, are called algebraic classes. And so the question of Borel and Effrigueux that Claire mentioned also this morning is the following. Let me recall. Which algebraic classes on X? So again, algebraic classes means classes that are linear combinations of classes of this type. Which algebraic classes on X can be represented as Z linear combination of classes of smooth subvarieties of X. Okay, so maybe I should add here algebraic to distinguish smooth algebraic subvarieties of X. Okay, so and what Claire proves this morning is that in the so-called Whitney range, this is always possible. So Kähler-Voisin. Okay, so I didn't, it's hard to say yes to this question, to answer yes to this question, but all algebraic classes when the dimension is small. Okay, so maybe, okay, so this was the aim of her talk. She also mentioned that there are counterexamples. That actually are much older than their result. And so maybe since I'll talk a little bit more about these counterexamples, I'll explain what they are. So there was, first of all, maybe not, I'm not so good about dates, so I'll just say, okay, so there's a Hartshorne, Rees, Thomas. So they gave, so a counterexample, when X is Grassmannian, so let me just introduce a notation. Okay, so I'll take a non-standard notation, but it's easier to write the results like this. So GRS is the Grassmannian of R-dimensional subspaces, vector subspaces of CR plus S. Okay, so this is a smooth algebraic variety, projective algebraic variety. Of dimension RS, and it has the property that all cohomology classes are algebraic. Okay, so we don't need to worry about the class itself being algebraic. Okay, so all cohomology classes Okay, so the question on this particular variety is, so you take a cohomology class, can you write it as a linear combination of classes of smooth subvariety of of the Grassmannian. And so the result is that when R and S are both at least 3, so notice there is a symmetry. GRS is isomorphic to GSR. So when R and S are both at least 3, there are codimension 2 classes So when I say codimension 2 classes, I mean classes of subvarieties of complex codimension 2, so they are in H4. That are not, maybe I'll just use the word smoothable, in the sense that they cannot be written as a linear combination of classes of smooth algebraic subvariety. Actually, they prove more, as Claire mentioned. They are not even, you cannot write them as a linear combination of classes of submanifolds, differentiable submanifolds of X here. And so the more precise result is the following. So it's classical that this group here is a free abelian group of rank 2, which is generated by so-called Schubert classes. You don't need to know what they are. So one of them is called sigma 1 square, and the other one is called sigma 2. And what they proved, actually using Tom's idea, which are really of topological natures, using Steenrode squares and stuff like that, they proved that any, let's say if, so A sigma 1 square plus B sigma 2 is the class of a submanifold, so differentiable submanifold. Then B must be even. Okay, so B must be even. So if you take linear combination of these classes with this property, the second coefficient must still be even. So in particular, sigma 2 is not smoothable in this strong differentiable sense. In what sense? Is exactly equal to? I don't know. Yeah. So Claire's question is whether the subgroup generated by classes of submanifolds is it equal to C1 square, sigma 1 square plus 2? I don't know. I don't know that. Yeah, I should say that these classes are classes that are multiples of sigma 1 squares are obviously smoothable. It's easy. Okay, and so the result that I want to discuss is the following. So the theorem is the following. So to state it, I need this notation that if m is an integer, alpha of m is the number of ones in the binary expansion of M. So you see that I need this notation for this very, in a very strange way. So our theorem is the following. So it's a condition of the codimension of the cycles. So as you see, it's a very, very strange condition. Strange, but still easy to check. And Okay, so we are far outside of the Whitney range. There exists X, a variety smooth of dimension n, and an algebraic cohomology class of codimension C, sorry, which is not smoothable in the algebraic sense. Okay, so this is what I call the non-smoothable cycle on an algebraic variety. So this is a very strange condition. It holds for this condition holds for certain values of C, infinitely many values of C, and the lowest ones are like this. Okay, and so in particular, it gives a negative answer. Well, I stated the question in the wrong way. I cannot answer yes or no, but it gives examples of non-smoothable classes when C is equals 2, for example, and n at least 6. And as Claire revealed this morning, the variety X here will be the Jacobian of a very general curve. Okay, so I'm lucky because Stefan also explained everything about Jacobians. So, okay, and so in terms of counterexamples to this question, there's a remaining case. The first remaining case in terms of the numbers C and N is when C is equal to 3, which completely this doesn't work. Our method doesn't work, and n equals 6. Because of previous results by people like Kleiman, Hironaka, this question is answered when n is at most 5. So the first cases begin in dimension 6. Okay, so I will explain. I will explain two things. The first one is you have to be careful with the water. So the first one is sort of another proof of the Hartschen-Ries-Thomas result, of a weaker form of this result that has to do with the representability of by classes of algebraic subvarieties instead of more generally submanifolds. And the second one, I will give a partial proof of a special case of the theorem. And you see that it's, I mean, the idea is that you compute a number that for some abstract reason needs to be an integer, and that gives you some numerical constraints on these coefficients, for example, in the case of the Grassmannian. So, so let's say it's a theorem, but it's really quite simple. So I did that with my colleague Frédéric An. So as I said, it's a weaker form of this, of the Hartshorne-Rees-Thomas lemma result, sorry. So assume Y is a subvariety. Maybe I called it, I think I called it Z, okay. Okay, so this is an algebraic smooth subvariety. I need to assume that R is at least 3 and S is at least 4. So that's another sort of weakening of the Hartshorne-Rees-Thomas result. And so write its cohomology class as I did earlier. Then B is even. So same conclusion as before. Sigma 2 is not smoothable in the algebraic sense. Okay? And so the proof follows 3 steps. I'll just describe the steps, not do the details. So first of all, so what I want to do is, forgot to say that of codimension 2. Nothing is new, it's weaker. Except the proof is simpler. Well, it's a consequence, but it's a different proof. It's a simpler proof. Okay, you don't need to know about topology. No, it's just that the proof is the same as the one I'm going to present in the second part. So the idea is that out of this subvariety of codimension 2, you produce a vector bundle on G, and then you just use the fact that the Chern character of this, you use the Groton-Dickerman-Rock theorem to obtain that some number is an integer. So let me go through the steps. So the first step is to produce this vector bundle, I want to use something called the Serre construction. So first of all, I need to prove that Z here is what is called subcanonical. And for this, I need a Lefschetz type theorem. Sorry. And so this is true, and so what is true? That this is surjective. And this holds, so this is where I need that R is at least 3, S at least 4, and Y Z smooth. Okay, so once you have that, you know that the canonical bundle of Z comes from a line bundle on G, and you apply the Serre construction, so-called Serre construction. I don't want to go into details, but this construction gives you a rank 2 vector bundle on G to obtain E, rank 2 vector bundle on G. I don't think so, no. I mean, this is what I... yeah, there's a whole series of a theorem like this proved by Bart van de Ven, Somese, and people like that some time ago. So obtain rank 2 vector model on GRS with a section whose zero locus is exactly Z. Okay? In particular, it tells you that the second Chern class of E is the class of Z, the class that I wrote as A sigma 1 squared plus B sigma 2. Okay. Okay, so now we need to do some computations. And to compute, it's hard to compute on GRS. And first I restrict E to G33. Okay, so here this is enough to have R and S both greater than or equal to 3. And you compute the following integral. So this here is the Chern character of the restriction times the third class of G33, and by Grothendieck-Riemann-Roch, this number must be an integer. You have everything that you need to compute this number. You need a computer, and so what you get is a big expression, which is a polynomial in A and B with rational coefficients. And so in particular, it begins. This is something which is so it depends on the parity of A. Here I write P of AB, but it's an explicit polynomial in A and B. And plus, you can always, upon twisting E with a line bundle, you can always assume that A is equal to 0 or 1. Okay? And you work out this condition, and so it's very easy to see that this implies that B is even. Okay. So it's just a numerical computation. Okay, so that's the end of the proof. Maybe some comments here. So this kind of, the first step has, the first step is only used to apply the second step. The circle construction only works for smooth subvarieties, or maybe more generally for locally complete intersection subvarieties. It is also likely that this, the first step A also works for when Z is a locally complete intersection, but we don't know how to prove this. But it's usually, for example, for subvarieties of Pn, this is true. Okay, if you have subvarieties of Pn with small codimension, then the Picard group is and this subvariety is a locally complete intersection, then the same kind of Lefschetz type theorem holds. So maybe if everything works fine, you could replace smooth in all these questions with a locally complete intersection. But we don't know how to do that. Okay, well, that's it for the Grossmanian. Yeah, I wanted to mention something that Kähler explained to me, which I think is very nice. You need to compute this number on GRS. I don't know. You're good at computers, maybe you can do it. I don't know, because you mean if you have a larger R and S, maybe you get a stronger condition on B? Yeah, maybe. I can ask Frédéric to do it. Yeah. I still have 15 minutes. Huh? No, I started 30 minutes ago now. You're very generous with time, but 15 minutes. It's dangerous to do that. Huh? Okay, so maybe people in the audience are very young, they don't remember the Hartshorne conjecture. So Hartshorne conjectured in 1974 that any subvariety, any smooth subvariety of Pn of codimension 2, say, when n is at least 7, is a complete intersection. So it's a very strong statement, and it's still open, and I think people have stopped working on this, maybe I could safely say. And so what Claire remarked, she remarked that the Hartshorne conjecture, the one that I just stated orally, would imply that any smooth, analogous statement on the Grassmannian, so any smooth codimension 2 subvariety of GRS, when R and S are at least 7, so the same bound as in the Hartshorne conjecture, is a complete intersection. So when I say complete intersection, I mean globally a complete intersection. So the transverse intersection of two hypersurfaces. So in particular, its class should be a multiple of C1 sigma 1 square. So the integer b that I used earlier should be 0. Okay, so it depends whether you're of an optimistic nature or not. You could say, well, this proves that the Hartshorne conjecture cannot be true, or I don't know. So this is interesting because if this is true, it means that the so really sigma 2, not only sigma 2 cannot be written as a Z linear combination of classes of smooth subvariety, but also not as a Q linear combination. So this is a Q version with Q coefficients of the Borel-Hefliger question, which I think is still open. Okay, so this was sort of a second part, and the third part would be a proof, but very sketchy, of the main theorem, the one with the other Olivier. Semi-obvious by Claire means not really obvious. But Thank you. Okay, so I'll explain this case of the theorem because it's nice because the first case was actually an old theorem of mine from '95. So I'll save time by not recalling what a principally polarized abelian variety is. So my notation, I'll still call it X and little theta instead of capital theta. I'll still use the standard abbreviation PPAV. So as Stefan explained, this is, let's say, of dimension G to, no, dimension N, sorry, this was to keep the same notation. And so this is Cn, the quotient of Cn by a lattice. So in particular, Cn is the universal covering of X. So the H1 of Xz is, so this is also the pi1, so therefore the H1 is gamma. And so it's not difficult to prove that actually Hi of Xz is the ith exterior power of the dual. So H1 is a gamma dual, and Hi is the ith wedge product of this. So in particular, so theta is a class in H2, and H2 is a wedge 2 of a gamma dual. And as Stefan explained, theta can be viewed as, so theta was the imaginary part of the Hermitian form that he introduced. Okay, and so this is a unimodular skew-symmetric form on gamma. So in particular, you can write it in a suitable basis as dx1, dx2 plus dx to g minus 1, dx to g. Okay. This is just to explain the fact that Stefan mentioned that if you take the cth power of theta, then it is divisible. And it's divisible exactly by c factorial. You can see by just raising that to the cth wedge power. And this class, the quotient of this class by c factorial, I will call theta c min. It's a minimal class. Okay, so it's not divisible in this group. So, so let me first state. I need to explain. I don't remember if Stefan explained this, but so the first remark is that theta to the cth power is algebraic. Because it can be represented as the intersection of the theta divisor with various translates of itself. So it is algebraic. This one is not known to be algebraic in general. And this is an important problem, as Stefan mentioned. There are several consequences to it be representable or not. But it is on the Jacobian of a curve, on Jacobians of curves. Okay, so the example that I will take is to take X to be the Jacobian of a very general curve of genus N. On this variety, we know that this class is algebraic, as I just mentioned. And we also know that any algebraic class is a multiple of this class. Okay. So in some sense, as in the previous example of Grassmannians, we control the algebraic classes. What we don't control is whether these classes are represented by smooth subvarieties or not. Okay. So here I said it is algebraic. We know even more. It is represented by a subvariety of the Jacobian. But when n is at least 6, this variety is singular. Maybe I can count the time that Claire took to answer as a question time. So the first version of our main theorem, I proved in codimension 2, I proved it in 95, and the proof is very similar to this one. So maybe I'll just keep it to see that it's exactly the same. Okay. So as I explained here, C is a very general curve. Of genus N at least 7, so this is not as good as the bound in the theorem. The smooth subvariety of codimension 2 then its class is an even multiple of the minimal class, which is just this class. And the proof is exactly similar. So this is, of course, before that. So same thing. There's a Lefschetz type theorem. Okay, and for this, we need Z smooth. But N only at least 6. Okay, so B, you produce E as above, vector bundle of rank 2 on the Jacobian with so let me equals the class of Z, which I will write as maybe B times theta square over 2. Okay, this minimal class. Okay. We don't know anything about the C1 of E, except that it's a multiple of theta. I didn't mention it, but this comes from the fact that the C is very general. And again, you compute this number, which I've now erased, that comes from the Riemann-Roch, Grothendieck-Riemann-Roch theorem. Except that since we're on an abelian variety, the third class is trivial, because the tangent bundle is trivial. So it is simpler. So again, we can assume that A is equal to 0 or 1 just by twisting E by a appropriate multiple of a theta divisor. And so by Grothendieck-Riemann-Roch, this is an integer. Okay, so now I'm not taking n equals 6 or whatever. I want to do it in any dimension because you cannot restrict to a subvariety of the Jacobian of C. There is nothing. Well, actually, you can do, but so let me give you an example. When n is equal to 8, so this is something you can compute. It's not very difficult. The Chern character is a bit complicated, but still it can be computed. So for example, when n is equal to 8, you get this. So the reason why this is giving non-trivial information is that the Chern character is a polynomial in the Chern classes with rational coefficients. There are denominators, okay? Otherwise, it wouldn't give you anything. Okay, so B must be even. You see, it's not so complicated. When n is equal to 6, what you get is some integer plus 9/4 and this unfortunately gives you nothing when a is odd. Okay, so it doesn't work when n is equal to 6. When n is for other values of n greater than or equal to 7, you slightly change the method, but it still works. Okay, so this is the end of the proof. So 4 minutes. So what can we do when n is equal to 6? We use a similar method, but with extra information, which is the following. On an abelian variety, actually on a, let me write it, on an abelian variety, the whole Chern character takes integral values, meaning takes values in the integral cohomology. Okay. In some sense, this is saying that the top part of the Chern character is an integer. This is a stronger statement, which is not true on any variety, but it's true here. And so this is actually a topological statement which comes from the fact that X is homeomorphic or even diffeomorphic to S1 to the power 2n. Okay, so I don't have to explain, I don't have time to explain, but so the thing is that the churn character factor through a topological churn character, and you prove that this topological churn character has this property. Okay, so it has nothing to do with algebraic geometry. Okay, and so in particular, when n is equal to 6, we can compute the not the top part of the churn character, but the degree 4 part. And we find that it is equal to Sorry? This is not known. Yeah, this is not known. I don't think so. Oh, this holds for any rank, yeah. Okay, so here we get again that, so this is a minimal class, so this the fact that this class is integral in H8 of XC implies that B is even. For higher codimensions, this method doesn't work at all. You cannot, as I explained earlier, you cannot use the cell construction, and you must replace here we use the K theory. Topological and algebraic to prove this, and you must replace this with complex cobordism. But in a sense, the method, the idea is still the same. You produce some expression that must be integral in some sense, and then you need to control the divisibility properties of these expressions. For example, the churn character this is very hard. Actually, the fact that the circumstructure doesn't work in codimension more than 2, it's not really an obstacle. What's more an obstacle is to control the denominators in the churn character. It's sort of not random, but wild. So maybe I'll finish on just one thing. In this example, as Claire explained, all the varieties that you construct here, all these minimal classes, sorry, are actually linear combinations of classes of submanifolds, differentiable submanifolds. And you can see that, as she explained, by degenerating the Jacobian to a product of elliptic curves. And then sort of the answer is obvious. This minimal class is just the class of a sum of various products of these elliptic curves. You just take all possible products in the codimension that you need. Okay, so this is not going to give a counterexample of the Hartmann-Ries-Thomas type. This is really an algebraic statement. And last remark, that on the Grassmannian, the churn character does not take integral values, so you cannot use this kind of method. Well, I guess I'll stop here. Thank you.